Today I'm going to solve the 24th challenge on Ethernaut called Puzzle Wallet. Scroll down. In this challenge, you are given a proxy wallet contract, and the goal of this challenge is to become the admin of this proxy wallet. I'll copy this code over to my code editor and also deploy this challenge. Okay, I'm inside my code editor and I copied the code over from Ethernaut. Let's take a look at the contract. Again, the goal of this challenge is to become the admin of this proxy contract, Puzzle Proxy. Now in this challenge, we are given two contracts, the Puzzle Proxy, and if I scroll down further, the proxy implementation called Puzzle Wallet. What this means is that the wallet storage will be inside the Puzzle Proxy, and there are some functionalities, but the main logic for the wallet will be inside Puzzle Wallet. The code inside here contains the code for the wallet, and this is the code that will be executed. However, since this is a proxy contract, the storage that will be used is the Puzzle Proxy contract. So how can we take over the admin state variable? I've highlighted it, and let's take a look at how we might be able to write to this admin state variable. Scrolling down, the only place that I see the admin being updated inside the proxy contract is by calling the function approve_new_admin, and to be able to call this function, we need to be an admin. So calling this function, we probably won't be able to win this challenge. Now, when we're dealing with proxy contracts, one bug that we should look for is whether the state variables in the proxy and the implementation contracts are declared in the same order. What do I mean by here? To show you this, I'm gonna split the screen into two parts. And then on the left side, I'm gonna show you the state variables for the Puzzle Proxy. And then on the right, I'm gonna show you the state variables for the implementation, the Puzzle Wallet. Now notice that for the proxy contract, for the first state variable we have pending admin, and for the second state variable we have an admin. However, in the implementation, for the first state variable we have an owner, and for the second state variable we have a max balance. What this means is that if we are able to update the max balance, then this will mean that we overwrite the admin state variable. So let's take a look at how we might be able to update the max balance. So I'm going to expand this Puzzle Wallet contract, and I've highlighted it. Let's scroll down and see where we might be able to update this state variable max balance. Scrolling down, I see that there's a function called set max balance. So if we are somehow able to update the max balance by calling the function set max balance, then this means that we'll be able to update the admin state variable and then win the challenge. Okay, so back to the implementation contract. How can we call this function? What are the conditions that we need to meet to be able to call this function? I see a modifier says we must be only whitelisted, and that is the only modifier that is attached to this function. And there's also another requirement that the balance of this contract, the if balance of this contract must be equal to 0. So those are the two conditions. We must be whitelisted, and the if balance of this contract must be equal to 0. Let's start with the first condition. How can we get ourselves whitelisted? So what I'm going to do is next highlight the whitelisted state variable, and then try to find a function where we'll be able to update this state variable whitelisted and whitelist our contract. I see immediately over here that there's a function called add to whitelist, and it says if message.sender is the owner, then we'll be able to whitelist this address. So how can we become the owner of this contract? Going back up, remember that the storage were misaligned between the proxy and the implementation. Inside the implementation, the first state variable is owner. However, inside the proxy contract, the first state variable is what's called pending admin. So if we can update this pending admin state variable, then this means that the owner state variable inside the implementation will be updated. Okay, so going back to the proxy contract, how can we update the pending admin? I'll highlight the state variable and then scroll down. And there is a function called propose new admin. If we propose a new admin, and this function looks like anyone will be able to call. So what we're going to do is call this function and then set the pending admin to our contract. When we do this, inside the implementation contract, the owner state variable will be updated. And once we become the owner, what else can we do? Well, let's check. Once we become the owner, we'll be able to call the function add to whitelist. And then once we whitelist our contract, we'll be able to pass the first condition for calling the function set max balance, which is that only whitelisted will be able to call this function. Let's put what we have discussed so far into code, and then later I'll discuss how we'll be able to bypass this condition that the if balance of this contract is equal to 0. So first, our goal is to get ourselves whitelisted inside the implementation. So what I'm going to do is scroll up. Actually, I'll close this window and then go back to the code editor on my left. And then we'll write our code inside here. Notice that below the cursor, we have an import and we don't have this code. Later, we're going to be deploying this contract using Remix. So I'm going to write my code above the import and then copy all of the code above this import and then deploy the contract. We're not going to be able to copy the code below. So I'm going to define an interface for the wallet. Define the functions that we're going to be calling for both the proxy contract and the implementation. So here is the interface that I declared. And these are the functions that I will be calling. Next, we'll create our hack contract hack, and then we'll write all of our code inside the constructor. Say constructor. It's going to take in the address of the proxy wallet. wallet, I'll name it wallet. And then our goal is to get whitelisted. So how do we do this? Recall that the first thing that we need to do is update the pending admin state variable. And this will let us become the owner of the implementation contract. So say wallet dot, how do we set the pending admin? Scrolling down, we call the function propose new admin. So wallet dot propose new admin, and we're going to propose that this contract should be the new admin. Address this. I'm going to open the code editor on my right again, and then scroll down to the implementation. And once we call propose new admin, we updated the pending admin state variable, and inside the implementation contract, this will be the owner state variable. So what this means is that we can now call the function add to whitelist. That's what we'll do next. So next we'll say wallet dot add to whitelist this contract. Okay, at this point, we're now the owner of the implementation contract. Going back to the implementation contract, we can now call the function setMaxBalance, but to be able to successfully execute this part of the code, the next thing that we'll need to do is withdraw all of the ETH stored in this contract. So first, let's check how much ETH there is inside this contract. To do that, I'm back inside Ethernaut, and then I'm going to type F12 to get the contract address. Type F12, and then copy the contract address. Next, I'm going to go to Etherscan for Gorby testnet, paste the address of the contract, and you can see here that this contract has 0.001 ETH. So that is the amount of ETH that we'll need to drain from this contract. How can we withdraw the 0.001 Ether locked in this contract? Let's scroll down and see if there's any function that sends Ether out of this contract. Scrolling down, I see that calling the execute will send some Ether out of this contract. And if I scroll down further, I don't see anything else. So let's put our focus on this function execute. How can we withdraw Ether by calling this function? What are conditions that we'll need to meet? Well, if I go all the way to the right, it says that we need to be whitelisted to be able to call this function. We already satisfy that condition, so we don't have to worry about it. The other condition is that the balance of message.sender must be greater than or equal to the value that we're withdrawing. So those are the two conditions. And to increase this balance, the function that we'll need to call is deposit. When we call the function deposit sending some ETH, this will update the balance, and to withdraw, we call the function execute. If we deposit 0.001 Ether, then the maximum amount of Ether that we can withdraw from this contract is also 0.001, and all the 0.001 Ether that is locked inside this contract, we cannot take it out. If we can somehow deposit 0.001 Ether, but update the balance to be 0.002 Ether, 0.001 that we sent, and the other 0.001 that is locked inside this contract, then this balance will be 0.002, and by calling execute, we'll be able to withdraw the 0.002 Ether locked in this contract. So is there a way to call the function deposit only sending half the amount of Ether, but being able to update the balance to the twice the amount that we send? Let's take a look at the function multicall. Actually, I'm going to close this window and then go back to the main window and then scroll down. And let's take a look at the function multicall. To call the function multicall, we need to be whitelisted, which we are, so we don't have to worry about that. It takes in the data to do a multicall. If I look over here, I can see that it is doing a delegate call on this contract. So what this means is that we'll be able to do a multicall on the functions inside this contract. And it's going to be using delegate call. Delegate call means it's going to execute the code inside here with the context of this contract. So the state variables and the amount of beef that was sent to this contract will be used to execute the code of this contract. This is kind of confusing, so let me put some comments. We're using the proxy contract, and then it's going to call this implementation contract, implementation, and then here it's going to do a delegate call. From calling the proxy to the implementation, we are doing this by calling a delegate call. And then from this implementation contract, again, we do another delegate call. So this will be another delegate call. Using multiple delegate calls will preserve the context. Let me explain. So let's say that A delegate call to contract B, and then contract B delegate call to contract C. When the code inside C is executed, which state variables are updated and what are the values of message.sender and message.value? Well, if A delegates call to B, let's say that a user sends 1 Ether. So user sends 1 ETH. And inside A, we know that message.value will be equal to 1 ETH. Delegate call preserves the context. So inside contract B, message.value will be also equal to 1 Ether. And again, we're doing another delegate call. So inside contract C, message.value will again be 1 Ether. How about state variables? Which state variables are we updating when we're chaining delegate calls? When A delegates call to B, it's going to execute the code inside B, but it updates the state variable of A. The state variable that is being updated is here. How about when B delegates call to C? When B delegates call to C, it's going to execute the code inside C, but updates the state variable of B. But the state variable of B points back to A. So as a result, chaining delegate call will update the state variable of A. So we found two things when delegate call is chained. The context is preserved to be the ones in A. So for example, message.value that we sent from here, inside C, it will also be equal to 1 Ether. And also when we chain delegate call, the state variable that is being updated will be contract A. So let's put this fact back into our case, proxy implementation. And then from implementation, we're doing a delegate call back to the implementation. So we said here that message.value, if we send 1 Ether, then inside C, it will also be 1 Ether. So applying this fact to our case, we are chaining two delegate calls from proxy to implementation, and then by calling the multi-call from implementation to implementation again, message.value will be the amount of Ether that we send to the proxy. And the other fact is that we said that it's going to update the state variable of contract A. So in this case, contract A will be the proxy contract. So with that in mind, let's take a look at the rest of the code for multi-call. Inside this for loop for the multi-call, we have a check that says that the call to deposit can only be called once. And the comment says it protects against reusing message.value. So what happens if we comment this part of the code out? And let's say that we do a multi-call to deposit twice. For example, let's say we send 1 Ether and then do a multi-call, call the function deposit twice. So the first time, it's going to do a delegate call and then call the function deposit. For this example, we said that we're going to send 1 Ether, so message.value will be 1 Ether, and it's going to call the function deposit. And then it will update the balance of our contract to 1 Ether. And then this will finish the first iteration of the multi-call. We said we're going to call the deposit function twice. Again, remember that we only sent 1 Ether. On the second call to deposit, let's go back to the deposit function. It's going to update the balance of our contract again, using the same message.value. So what does this mean? By using multi-call, we only send 1 Ether, but we can update the balance to be twice what we sent. So if we can somehow send 1 Ether, and then using multi-call, call the function deposit twice, then we can send 1 Ether, but then update the balance to be twice the amount of Ether that we sent. So is there another way to call the deposit function? So let's put this condition of checking that deposit can only be called once back. and try to see if there's another way where we can call the function deposit. Let's say that for the first call to multi-call, we call the function deposit. For the next call, how can we call the deposit function again? Well, how about for the second call to multi-call, we call multi-call again, and then inside that multi-call, we call the deposit function. And in that case, we'll be sending 1 Ether, but then calling deposit twice, and we'll be able to update the balance to more than what we sent. So what do I mean over here? So we're going to be calling multi-call, and for the first multi-call, we're going to call deposit, and then for the second multi-call, so this will be the second data inside this data array, we're going to do a multi-call, and then inside the second multi-call, we'll store 1 call to deposit. As a result, when we call the function multi-call, we're going to be calling 2 multi-calls. And since the deposit call check is reset every time we call the function multi-call, we'll be able to bypass this check. So let's put this in code. I'll cut this comment out and then go to top and then paste here. And this is the data that we need to prepare. Let's prepare the data to call deposit. So I'll say bytes, memory, I'll name it deposit data. This is equal to new bytes of length 1. And then type deposit data of 0 is equal to abi.encode with selector wallet.deposit.selector. Next, we'll prepare the data for multi-call. So type bytes array memory data is equal to, inside the data for multi-call, we'll be putting 2 datas, deposit and then another multi-call. So this will be a bytes array of length 2, new bytes of length 2. The first data will be a deposit, so say data 0 is equal to deposit data of 0. And then the second data will be a multi-call with the deposit data again. So the data of 1 is equal to abi.encode with selector wallet.multicall.selector with the data deposit data. And once we're done preparing the data, we'll call wallet.multicall, passing in the data. And earlier we said that this wallet contract has 0.001 Ether. We'll also deposit 0.001 Ether, but since we call deposit twice, our balance will be 0.002 Ether. And after we call this function, we'll be able to withdraw the 0.002 Ether that is stored inside this wallet. Value 0.001 Ether. Okay, next, after this part of the code executes, there will be 0.002 Ether in the contract, and our balance will be 0.002 Ether. How do we withdraw that Ether? Scrolling back down, the function that we'll need to call is execute. So I'll copy this and then paste it here. So this is the function that we'll need to call. So say wallet.execute. Who should we send the Ether to? Well, it can be either this contract or we can send it back to message.sender. Message.sender. This will be our account. How much Ether are we withdrawing? All of it, which will be 0.002 Ether. And what is the data that we want to pass to this function execute? We don't really care, so we'll just pass the empty data. Okay, once we call this function, the Ether balance of the wallet contract is 0. So finally, we can call the function setMaxBalance. So I'll copy this function and then paste it here and then type wallet.setMaxBalance. And again, by calling setMaxBalance, we update the admin, and we want this admin to be message.sender. So say message.sender, but we'll need to cast this to uint 256. So we'll do that by first casting it to uint 160, and then casting the uint 160 to uint 256. Okay, we're almost done. At this point, we have now claimed the admin to be our account. Let's double check. Require wallet.admin is equal to message.sender, else I'll type hack failed. And when we call this function, we're going to need to send some Ether. So I'll declare the constructor as payable. And then at the end, whatever remainder ETH that is locked inside this contract, we'll do a refund to our account. So say self destruct to payable message dot sender. And that completes the contract. Next, I'm gonna copy this part of the code, paste it over to Remix. Okay, let's try compiling this contract. I'll hit Ctrl S and the contract compile. So I'll click on the deployment tab, make sure that we're connected to the Goerli testnet. So do that by clicking on injected provider MetaMask. Next, we'll deploy the hack contract and passing in the address of the wallet. The address of the wallet, I still have my Etherscan open, so I'll copy this, paste it inside here. And before I deploy the contract, I'll need to send some Ether. I'm not worried about the amount since I'll get it refunded. So I'll just send 1 Ether and then click deploy. Okay, the transaction was successful. The last step is to submit our instance back on Ethernaut. That completes this level. See you in the next one.